Hey programmers, I'm Alvin from CoderByte, and welcome back to our course on data structures and algorithms. In this episode, what I want to do is introduce us to the topic of binary trees. It's a really important topic, and we'll start covering it over here. So we have a few things to cover on today's agenda. First and foremost, what I want to do is define the term binary tree. That way we know what to look out for when we have a binary tree problem. And we also want to end up implementing a breadth-first traversal. And that'll actually be our first algorithm we perform on a binary tree. And so let's start with some basics. What is a tree in the computer science meaning of the word? Well, a tree is going to be a collection of nodes and edges. Typically, you'll see images of trees where the nodes are circles and the edges are lines that connect those circles. There are two main characteristics that really identify a tree. The first one being that a tree should have a root node, and we'll see what that means in a little bit. But short story is the root node is the single node of the tree from which all other nodes are accessible. And the second property of a tree is that there only exists a single path that's unique between any two nodes. So with these 2 points in mind, let's go ahead and look at some examples. So here's an example of a tree. What you'll notice is these circles with the letters inside of them, that represents our nodes, and the arrows are the edges or connections between those nodes. In this particular example, the A over here happens to be the root node, right? That's because it's like the topmost node where no other nodes actually point to A. So I designate it as the root node. What you'll notice about a tree like this is it really shows the picture of a hierarchy among the nodes. For that reason, it's very common to use familial language when describing the relationships between the nodes. So for example, there are a few statements I can make about this tree. I can say something like the A node has 3 children. Those children are B, C, D. I can say the nodes B, C, D have the parent of A. I can say things like C and D are siblings. I can say that C has 2 children and D has 1 child. Now that we have a few ways to talk about trees, we know that A is the root node because it's a node with no parents, right? There's nothing that comes before the A node over here. In a similar sense, we can talk about nodes B, E, F, and G. Those are the leaf nodes, right? B, E, F, and G are leaf nodes because they have no children. Another term that you might hear when referring to trees is level. So what I can say is these nodes B, C, D are all on the same level. In the same way, the nodes E, F, G are all on the same level. And I can assign numbers to these different levels. I'll say that B, C, D is on level 1 because all of those nodes are 1 edge away from the root. In a similar sense, I can say that the only node on the root level or on level 0 is the root node A itself. In a similar sense, E, F, and G are on level 2 because all of those nodes are 2 edges away from the root. When we refer to the height of a tree, we're really just referring to the largest level. So if I talk about the height of this particular tree, that would be 2 because the largest level is 2. So now that we've seen an example of a tree, let's go ahead and look at what is not a tree. So here's an example of a non-tree, and take a moment to analyze the structure of this diagram and kind of figure out why it's not a tree. So if I recall our properties of a tree, it should have really 2 main properties, right? It should have a root node, and it should also have a unique path between any pair of nodes. So if I look at this tree, I guess I could consider X the root node here because X can access all the other nodes, right? It can access Y and it can also access Z. So it makes sense that X is the root node maybe, and it also has no parents, which is a perfect fit for our definition of a root node. That being said, this tree structure does not actually satisfy our second point, right? I must have a single unique path between any 2 nodes. One way to get from X to Z is just going directly, right? Just go simply X to Z through this edge. And another way to get from X to Z is actually to flow through Y. So I can go X, Y, and then into Z over here. And because there's actually more than one way to get from X to Z, this is not a tree. So let's take a look at another example of a non-tree. Looking at this diagram, I guess we can consider the P node as the root because it has no parents, but this tree also does not satisfy the second property, right? So let's say I'm considering 2 nodes, Q and S. One way I can get from Q to S is just go Q, R, S, and another way is to go from Q to R to S to Q to R to S again, right? So technically, because there's like a cycle that we can travel through in this tree, there is not just one unique path that joins 2 nodes, right? There's really an infinite number of paths, we say. So by definition, if something has a loop or a cycle in it, we know that it's definitely not a tree. Let's take a look at one final example of a non-tree. So looking at this diagram, I'd say this is not a tree because there's not really a single root here. It looks like both nodes T and nodes U have no parents, and a tree should only have one single root. We need like an ultimate ancestor. So by now, you probably have it in your mind that a tree usually looks like something of like a triangle shape, where we have our root node at the tippy top. However, that may not always be the case. I'm going to argue that these two different pictures really represent the same tree. All right, so now that we know what the word tree refers to, what is this actually useful for? Well, it's really the case that because a tree represents a hierarchy, it's actually just a really nice way we can represent a hierarchy, and that actually shows up in many different instances. So for example, let's say that you're dealing with your computer's file system, right, where you have a folder containing many files, and you can even have a case where folder contains other folders. That actually looks like a tree, right? You can imagine that the different nodes of the tree in this scenario represent either folders or files, right? If something is a folder, then we know it could point to something else, in which case it has children. If something is a file, then it can't have any children, so it must be a leaf, right? So here I have just like the file system kind of sketched out on one of my folders on my computer, and we see that it definitely has some hierarchical tree structure, right? Hierarchies show up a lot in the real world. For example, I could use a tree to represent the reporting structure at some company, where I have the CEO at the top and then maybe the junior engineers at the bottom of that tree. So trees are very, very useful, and we'll use them a lot in this course, but right now I want to turn our attention to a particular flavor of tree, and that would be a binary tree. So what is a binary tree? Well, it's definitely a type of tree, so all of those old properties still hold true, but it also has this additional binary criteria. And so that new property refers to the fact that it's a tree where every node has at most 2 children. So right now we're capping the number of children a node has to at most 2. And that really means that it could have 0, 1, or 2 children, right? It doesn't have to be exactly 2 children. So here I have 3 examples of binary trees. Looking at the first tree over here, we know it's a binary tree because it does follow the fact that a node has at most 2 children, right? So it's okay for a node to only have 1 child. And it's also okay for nodes to have 0 children, of course, in which case they're just leaf nodes. Also, this is definitely a binary tree, and even a lone node is still a binary tree because, right, it has 0 children and 0 is less than 2. So like you can probably imagine, there are some variations on the binary tree property, right? I could have a trinary tree, in which case nodes have at most 3 children, or I can generalize that to an n-ary tree where my nodes have at most n children. So with all that background info out of the way, let's go ahead and get to the good stuff. I want to implement a binary tree right now. So let's jump right in. We know that a tree contains many nodes, and so we can attack this in an object-oriented way by maybe creating a node class. So specifically, this node class I create right now is perfect for creating a binary tree. So we'll find this somewhat similar, I guess, to how we would create a linked list. So I'll create my constructor. Inside my nodes, I'm going to store some values, and I'll need, I think, just 3 properties, right? I'll need to store my target value. Then I'll also have properties for my children, right? So I can say this.left equals null, and this.right also equals null. It's very typical in a binary tree implementation, since you only have at most 2 children, to label them as your left and your right child. So just to clarify, right now I'm talking about plain old binary trees. That means I'm not talking about balanced trees, I'm not talking about search trees, I'm not talking about heaps. It's okay if you have no idea what any of those terms mean. We'll go over all of those more advanced data structures later on, which will use a tree as their basis. But for now, we're keeping it very simple. I just have a plain old binary tree. And that's actually great that we go over this because many of the problems that you'll encounter for your interviews will actually have you take in a binary tree as the input. So one way I can just construct a tree for myself is just to create some node instances. So I'll say things like A is a new node whose value is the letter A. Of course, you can store any values you want, like numbers if you wanted to, inside your nodes. For now, I'll just use characters. And I'll create a few of these nodes. All right, so here I have 6 node instances created, but how can I actually join them together? Right? I need to assign these left and right properties. Let's say right now I wanted to form this tree, right? So I want a tree of this structure. You can imagine that all of these edges kind of point downward, right? What I can do is just assign the pointers for left and right. So I can say something like a.left equals b, and also a.right equals c, and I can just do an assignment to represent every single edge of this drawing. So I think these 5 assignments should recreate this tree I have above. And that's all there is to it. Now that we have a tree that we can work with, let's actually implement our very first algorithm on a binary tree. So right now I want to introduce us to the breadth-first traversal algorithm. So breadth-first traversal is a way that we can access every value or every node of a binary tree following a particular order. The word breadth in this instance really refers to the width of the tree. So what I'm looking forward to is seeing an order where we flow across or going from left to right through our tree. So what's really characteristic about a breadth first traversal is I start at the root and I explore all nodes in the same level before I go downward, right? So the first thing I explore here is A, and now that there's nothing else on this level, I go to B and C, right? I explored everything on that BC level, and then I go down to D, E, and F. So the really important pattern I need is I need to be sure to explore across a level fully before I go down to the very next level. Overall, that gives you this order for this particular tree of A, B, C, D, E, F. So now that we know what breadth first traversal is, how can we actually implement it? Let's come up with a strategy. What's really great about breadth first traversal is it actually requires something we learned previously. We can implement a breadth first traversal through a binary tree using a queue. So recall that a queue is a data structure, right? Where I add things to the back of the queue and remove things from the front. And by simply sticking and committing to these queue rules, I'll get exactly the order in this diagram, right? So I should end up with A, B, C, D, E, F in that very particular order. So let's start the algorithm. What we say is at the start we have an empty queue, right? So there's nothing. Here I just have designated my front and the back, and I also have some things to print out. So as we actually touch the nodes of this particular tree example, I'm going to show you the order that we print them down here at the bottom. So what we'll want to do is initialize our queue with just the root node, right? So I put the root in my queue. So here I have A on the queue. And what I do is on every iteration of this algorithm, what I should do is just remove the front of the queue. So that right now means I'm removing the A node, right? A is the only node in my queue. So if I remove something from the queue, that's when you consider explored. So I just printed out A. And what I should do now is consider that printed node's children, right? So I want to look at A's children. In other words, I look at B and C and I add them to the queue. If I add them to the queue, then now it's the case that B is at the front and C is slightly behind B, right? So that actually ends my first iteration of the code. So here I have B and C on the queue. I'm on to another iteration. And what I do is, again, I just remove the front of my queue. So I remove B. That means I print out B. B's my current thing I'm looking at. And I look at B's children. So right now I look at D and E. If I look at D and E, that means I should add them to the back of my queue. So because I'm always adding to the back, D and E actually appear behind the C. So I'm done with that iteration of my breadth first. And now I have C at the front, in which case I remove the front always, right? And right now I'm exploring C, so I print it out over here. And I look at C's lone child, which is F, and I just add F to the back of the queue. And this algorithm continues all the way throughout, right? Now D is at the front, so I remove it, and I print it out. D has no children, so I don't add anything to the queue. Same thing for E. E has no children, so I just print it out. And finally, F has no children, so I just print it out. And by the end of the algorithm, my queue would be empty, so I know that I must have explored every single node of the tree. And this is exactly our breadth first order over here. All right, so let's code this one up. So I'll define this function. I'll call it breadth first print. So I just want to print out my node values along the way. And here, my function is going to take in the root of a tree. So basically, when someone is going to call this function, they're going to call breadth first print, and they should give me the root. In my particular tree example, that would be the A node over here, right? That'd be the root of this tree. Cool. So let's start to translate that depiction into some actual code. So I know that I definitely need a queue. For now, I'll just use an array because it's really easy to implement in JavaScript. And what I'll do is I'll initialize this queue with the root, right? That gives me a nice starting point, right? And initially, you really only have access to the root. So now that I have this queue, how long do I actually want to run this algorithm? Well, if you caught the drawing, we know our algorithm was done when the queue was empty. So I want to keep doing stuff while the queue is not empty, right? So I'll say while queue.length is greater than 0, then some things still need to be explored, so keep on exploring, right? So now that I have this while loop established, I want to focus on what happens on a single iteration of the algorithm. If you recall from our trace, what we do is we start by removing the front element of our queue. So using JavaScript, I could say queue.shift. So in general, queue.shift will remove the first element of an array, right? And queue is just an array, and it will also return that element. So I'll save this as a variable. Maybe I'll call it my current. So a really important detail to keep in mind when you're implementing a breadth first print or a breadth first traversal is when something leaves the queue, like queue.shift over here, that thing that you just removed is now being explored, right? So you only get to consider something visited when it actually leaves the queue and not when it's added to the queue. So now that my cur just left the queue, I'll want to explore it. For me right now, that just means printing it out to the terminal, right? So now that I've taken care of my current node or whatever was at the front of my queue, I need to add its children only if they exist though, right? So here I want to do a little preemptive check. I'll check, hey, if current has a left, so in other words, if current.left is not equal to null, then that node exists. So I'll just add that node to the back of my queue. So that'll just be queue.push of cur.left, and it'll be symmetric for the right-hand side. And that's actually all there is to this algorithm, right? These if statements basically just say, hey, if my current node has a left child, add it to my queue, and if my current node has a right child, also add it to the queue. By using if statements like this, I already automatically handle scenarios where a node only has one child or may have no children, in which case we know that it's a leaf. So one thing I'll also add into the mix now that I see it is I want to print out just the node values. So I just want to see the characters of the tree in this scenario. So I'll save this code, I'll give it a shot, and we should get the order of A, B, C, D, E, F. Remember that we're moving across an entire level before we go down to the very next level. So let's give that a go. Nice, and there we have our implementation of a breadth-first traversal. This is very, very common code to use in further problems, and I consider breadth-first a super duper important algorithm that you should definitely know how to implement offhand. So because breadth-first traversal is a very common algorithm that actually is going to be used in the solution for other problems, let's actually see one of those types of problems. So here we're going to implement a breadth-first search. So in particular, we're going to be given the root of some binary tree and also some target value. What our function should do is return a Boolean indicating whether or not the tree contains that target value. So for example, here they give us a tree of this particular shape, right? Same tree as before. And when they call BFS and they give us the tree, so they're giving us the root node and they give us some target value, we have to say yes or no or true or false, is that value within the tree? So here, E is in the tree, so we return true. In this other scenario, Z is not in the tree, so I return false. And it's very obvious where breadth first is useful here. I can use breadth first as a way to just look at every single node of the tree. Once I find the value I'm looking for, I can just return true early, and afterwards I'll return false if I don't find any such value. So to implement this one in a pinch, I can just steal basically all of this breadth first print code, and I can just add a little search quality into it. So that should just be as simple as a conditional. So I'll rename this function, we'll call it breadth first search, BFS. I'll take in the root node and some target. And a key detail here is where should I actually check for the target? I think the cleanest place to do that is just to check when something leaves the queue. You know that eventually every node's going to leave the queue. So over here I'll check, maybe over here actually, if my current node's value, or the one I just removed from the front, if that is equal to my target value. And if it is, then you're good to go and you can just return true and you're done with this function, right? There's no reason to look further in the tree. That being said, where do I return false? Well, that basically should happen after the while loop, right? Only after I've checked every node of my tree can I actually safely say that, hey, the value we're looking for is not anywhere to be found within that tree. So I'll return false over here. So if I run this code, I should get a true and a false. We'll give that a little test run. True, false. Nice, and there we have a very quick solution to breadth first search. Basically no work at all if you're very familiar with the core breadth first algorithm. Let's take a look at another simple example. Here they're also giving us the root of a binary tree, but this time around the tree contains number of values. What my function should do is return the total sum of all values in the tree. And we can also assume that the tree only contains number values. So imagine we were given this particular tree. We should return the number representing the total sum. So basically the sum of all the numbers over here should be 19. And you guessed it, I can just solve this with a very, very simple breadth first search. And what I can do is just keep a running sum as I go. So like before, we'll just steal this breadth first code and I'll adjust it for exactly the pattern we need. So I'll rename this as my sum tree. Still taking the root, don't need some target this time. I don't need this conditional. That was from my breadth first search. Basically, as I hit every current node, I wish I had some sum, which I should declare as a let. Initialize that to 0. As some node leaves the queue, I'll be sure to add its value into my sum. So sum plus equals current dot value. Again, just very, very minor manipulations around our base breadth first code. That's why this is a so important algorithm to really know how to implement offhand. I think a lot of students may actually struggle with implementing an algorithm like this because they haven't actually ever implemented a plain old breadth first traversal previously. So it's definitely a pattern I would really try to drill into your head. So let's give this a test run. I want to be sure that I return the total sum by the end of my function, and I should get 19. Cool, and there we have it. So as you can see, breadth first is a very useful algorithm. Let's talk about the time complexity of this code. So if I just look at like my core breadth first pattern that just accesses every node of a tree, the time complexity of this is going to be O of n, right? If we consider n as the size of the tree or n as the number of nodes in the tree, then I know that over time, I'm going to have exactly n iterations, right? Because every node of the tree leaves the queue exactly once, right? I will never do something weird like add the same node twice because I know that I have only one way to get to a node, right? Because it's a tree, right? There are no cycles or anything weird like that. It's also the case that the space complexity of this code is going to be O of n because of the queue that we use, right? We know that there's no possible way that the queue can have more than n different elements on it. So that means we have O of n time and O of n space for our regular breadth first print, O of n time and space for our breadth first search, and also O of n time and space for our sum tree. So that about wraps up this episode. What we did was define binary trees. So remember that binary means there is at most 2 children for a node, and tree means that there's only a single root node as well as a unique path between nodes. Along with that, we explored the breadth first algorithm and went over a few problems that actually utilize that core pattern. In the next lesson, we'll go over a very similar algorithm, and that would be our depth first traversal. So stay tuned for that.